Alright, welcome back to Organic Chemistry. This is part 3 in an extended presentation on nuclear magnetic resonance. In part 1 we learned a little bit of the background of NMR, and we saw how NMR worked with carbon-13 NMR. That is, we saw that carbon atoms, when placed in an external magnetic field, could be excited and relaxed, and the energy of that process could be measured, and that would tell us different things about the molecule. In part 2, we went on to see how we could put that information together to solve the structure of organic molecules. In this part, we're going to look at a different type of NMR, of nuclear magnetic resonance, and that's hydrogen NMR, also known as proton NMR. I'm usually going to say proton NMR. But remember, nuclear magnetic resonance is based on the magnetic moment of a nucleus. That is, charged particles that are spinning have a magnetic moment. And particles that have either an atomic number that is odd or a mass number that is odd have a spin. So carbon-12 does not have a nuclear magnetic moment, but carbon-13 does. And so in carbon-13 NMR, that's what we were looking at. But hydrogen has an atomic number of 1. Excuse me, an odd atomic number. And therefore all hydrogens are observable in the NMR. So here's an example of a proton NMR. And before we even get into the details of this, we're going to notice a couple of things that are different from the carbon NMR. For one, you'll notice that the x-axis has a different scale. Carbon-13 NMR went from 0 to 200. Here we're going to look at a region that is only 10 parts per million wide, so it's got a scale of 0 to 10. The other thing you notice is this looks a lot more complex than the carbon-13 NMRs that we saw. Carbon-13 NMR, certainly decoupled carbon-13 NMR, has just single lines. But here there's, messy patterns, almost always. So proton NMR is a little harder to read, in my opinion, than carbon-13 NMR, just because you have this added difficulty thrown in of always having splitting. We'll get to splitting in a bit. Which is why, by the way, when I go through things, I start with the carbon, because I think it's easier and just more straightforward. As I go on, I go to the more complex things, because I'd rather start out with the clear and end with the unclear. But let's dig into this proton NMR. There are going to be some things the same and some things different from what we saw in carbon NMR. The theory is the same. Nuclei, hydrogen nuclei in this case, are surrounded by electron density, and depending on different patterns of bonding. Now, hydrogen's always the same s orbital, it's always the same hybridization, but what they're connected to is going to differ. We will see signals at different places along the x-axis. But I am not going to do what I did with carbon-13. I'm not going to start by simply counting the signals, because in hydrogen NMR there are inevitably going to be patterns, and therefore it's hard to simply just count the lines and say, oh, I definitely have this many signals, and that tells me something about symmetry or not. So I'm not going to bother considering in the proton NMR counting lines to see if I have symmetry. The other thing is there's almost always symmetry that relates hydrogens to each other, because if I've got a CH3, those 3 hydrogens are related to each other. If I have a CH2, those 2 hydrogens are related to each other. Usually, but I'll just leave aside that for the moment. Sometimes there's cis-trans issues that makes them different, but let's leave that aside. So the first thing I'm really going to look at in the proton NMR is the chemical shift. That is, where the signals come along this x-axis tells me about the bonding environment. Specifically, it's going to tell me what that hydrogen is connected to. Usually, not always, that hydrogen is connected to a carbon. But different carbons have different orbitals, and therefore we're going to see different patterns of electron density close to the hydrogen, and therefore we're going to see different energies for the excitation-relaxation process. So for instance, in the top I have a spectrum of 2-methylbutane. And you'll notice all of the signals are over here. In the bottom, I've got the spectrum of styrene, and notice all of the hydrogen signals are down here. Here, I've got hydrogens on these carbon atoms. Here, I've got hydrogens on these carbon atoms. One thing that should jump out immediately is that these are all sp3 hybridized carbons, and these are all sp2 hybridized carbons. And notice the hydrogens that are attached to the sp3 hybridized carbons come in a different region than hydrogens attached to sp2 hybridized carbons. So before we know anything else about chemical shift, we can basically break the spectrum down into hydrogens attached to sp3 region and hydrogens attached to sp2 region. But we can actually go a little further than that, because it turns out that not all sp2 hybridized carbons are alike. In styrene here, I've got an aromatic ring and I've got an alkene. These are a little bit different, because remember, because of resonance, these double bonds are really delocalized around the ring compared to these. Here there's just a double bond between these two, but really this double bond is spread amongst this position, this position, this position, this position, and this position. And those turn out to come at slightly different areas. There's kind of an aromatic ring area and an alkene area. You look at a bunch of examples, you'll notice this. Now, they are kind of a fuzzy boundary between these. But within that hydrogen attached to sp2 hybridized carbon region, there's really sort of 5 to, say, 6.5, maybe even all the way to 7, a region for alkene hydrogens, and, say, 6.5 to 8, area for aromatic hydrogens, that is, hydrogens attached to something like benzene. And that's going to be very useful, because this can help us study the structure of molecules. There's also an effect of other elements. If we have strongly electronegative elements, that's going to play a role, just like it did in the carbon-13 NMR, because those strongly electronegative elements will sort of pull electron density away. So in this top instance, notice our hydrogens here are on sp3 hybridized carbons, and we've got a bunch of signals in what is really 0 to 4 is kind of the sp3 region. Let me restate that. It's the region for hydrogens that are attached to sp3. Whereas this other molecule, there are hydrogens here on an sp3 hybridized carbon, and notice there's a signal over here. But there's also hydrogens here, here, and here on sp2 carbons. And within this region, some are more to the left and some less to the left. Within this region, some are more to the left and some are less to the left. And as with carbon-13 NMR, being near a strongly electronegative element will shift you to the left. So this signal, for instance, is for the CH2 that's next door to this oxygen. This signal is for the CH2 that's attached to this nitrogen. Because nitrogen is not as strongly electronegative as oxygen, it's shifted a little more. It's a little to the left. Sorry, it's shifted less compared to the one by oxygen. These guys are for the ones in the middle. In this case, notice we have hydrogens on sp2 hybridized carbons, but this signal is way over here. Well, this hydrogen is on an sp2 hybridized carbon with oxygen. So this aldehyde proton comes more like 9.5 or so, as opposed to these alkene hydrogens. There's an H here and an H here, which are coming between 6 and 7. Now we have to be a little cautious. There's something that's in these molecules, or at least in the top molecule, that we didn't see in the carbon-13 NMR. Because in the carbon-13 NMR, we were looking at carbons. Here we're looking at hydrogens. But hydrogens are not necessarily just connected to carbon. They might be connected to things like oxygen and nitrogen. And it turns out that protons on heteroatoms, and hetero just means other, and to organic chemists that means stuff other than carbon. So heteroatoms really refers to things, elements other than carbon and hydrogen. So protons on oxygen, nitrogen, sulfur, phosphorus, boron. Those also show up in the hydrogen NMR. Notice those didn't show up in the carbon NMR, because if I was looking at the carbon NMR of this molecule, I would just see signals for this carbon, and this carbon. But here I'm looking at signals for the hydrogens. Notice I have hydrogens here, and hydrogens here. Where do these come? These are sp3 hybridized carbons, and so the signals for the hydrogens attached to them are over here. Those are those two signals, and we can talk about the patterns in a moment. But then there's this kind of blobby signal out here. That's one thing we'll notice about protons that are on heteroatoms. The signals tend not to be nice sharp signals, and they tend not to have these patterns of doublets and triplets, etc. They tend to be more rounded blobs. That has to do with hydrogen bonding and how things associate in solution. But the other thing is, these signals can come really over a relatively wide range, depending on the solvent. Again, if the solvent hydrogen is a hydrogen bonding solvent, it will interact with this group specifically compared to in a different way than if it was a non-hydrogen bonding solvent. It's also going to depend on the pH. If I'm under acidic conditions, this will be at one area, and if I'm under basic conditions, it might be shifted relative to that. And also concentration is going to affect those as well. So these signals can come really anywhere. Oftentimes they're pretty easy to pick out just because they're more rounded and sometimes low. Sometimes they're hard to see just because they are so low in a messier spectrum. And here you can see that spectra can have some noise. If I had a noisier spectrum, that might be buried underneath the noise. So we can sum up chemical shift. As with carbon-13 NMR, yeah, you could look up tables. There are books full of tables. I don't want you to do that. I want you to learn basic trends. Hydrogens on sp3 hybridized carbons come more to the right, say 0 to 4 or so. Hydrogens on sp2 hybridized carbons come more to the left, say 5 to 10. Within those regions, electronegative elements will shift things. So if you have a hydrogen on a carbon by oxygen, that's different than a hydrogen on a carbon by carbon. There's also some distinction between alkenes, hydrogens on just double bonds, and aromatics, or arenes. That's another word for aromatic things, which is things like benzene. That's hydrogens on sp2 hybridized carbons involved in delocalized, that is, spread out by resonance pi bonds. OHs and NHs throw a little bit of a wrench in the work in that they could come over a relatively broad range depending on the conditions. Hydrogens on an sp hybridized carbon, which really happens very rarely. That is only when you have what's called a terminal alkyne. That is one where the triple bond is at the end of a chain, and so you have a CC triple bond where one of the carbons has a hydrogen. Those come around too, which is a little unfortunate in that it comes in the same region as the hydrogens on sp3 hybridized carbons, but alkynes are relatively rare, and terminal alkynes is a smaller set of things than alkynes, so that's not something we're really going to be all that concerned about. So the first thing I'm going to look at in the proton NMR is chemical shift, because chemical shift is related to the bonding near that hydrogen. The second thing I'm going to look at is something that we didn't see in the carbon-13, and that's called integration. In carbon-13, the size of the signals, it didn't tell you a lot. Well, I mean, that's a bit of a lie. it's affected by a few different things. And so therefore, we didn't, when we went through carbon-13, we didn't say, oh, taller signals tell us this and shorter signals tell us that. But it turns out in proton NMR, the size of the signal tells us something pretty directly. It tells us how many hydrogens that signal represents. So, for instance, let's look at this molecule. Methoxy, 2-methoxy-2-propane, or methyl T-butyl ether is another name for this. You use that in lab as a solvent. It's also sometimes used as a fuel additive, MTBE. Okay, this molecule, because of symmetry, is going to have two signals. These hydrogens are all going to give one signal, and these hydrogens are going to give another signal. Well, there's more of these than there are of these. There's 9 of these, and there's 3 of these. If I look at this, I see that my signals, ignore that, that's just the 0 marker, these two signals are different sizes. And it turns out the ratio of sizes turns out to be, well, the ratio between the number of hydrogens. We're not just going to look at height, because unfortunately these aren't just lines. If we looked at these, you see that there's some width. They're really triangles. Okay, this is really a very tall but narrow triangle. And so what matters is not the height, but the area. The area of this triangle compared to the area of that triangle. In calculus, when you talk about curves and you talk about the area under the curve, that's the integral. You can integrate a curve over a region and figure out the area underneath that curve. And really, that's what's going on here too. We look at these as curves, and we can integrate from here to here, and we can integrate from there to there. Sometimes, due to the way that the instruments are set up, what you'll see in the integration is actually just a line that then just keeps going up. And then you can break that line into pieces, and so you have a little rise that's due to this portion and a rise that's due to this portion. And so what you'll say is that the heights of these rises, so from here to here, and the height of from here to here, is the ratio between these rises is the ratio between the areas under the curve, which is equal to the ratio between the number of hydrogens represented. Excuse me. Pardon me for that. Sorry if I just blew out your headphones if you're listening to this on a headphone. The ratio, if I was to take out, in this case, a ruler and measure it, or more realistically, the computer gives me a value for these, because this is all computer. This is all done on a computer screen now. Back in the day, this was all printouts, and you would actually take out a ruler and measure from here to here, and measure from here to here. But in a modern setting, you would get a value. But that value is really not the thing that we're looking at. The thing we really want to look at is the ratio between these. And the ratio in this case between 333 and 1000 is really a 3-to-1 ratio. Yeah, I mean it's really a 3.001 to 1 ratio or whatever. But I mean we're going to round that to whole numbers. And we see that this is a 3-to-1 ratio. That is, this peak is worth 3 times as many hydrogens as this peak. But my molecule doesn't have 4 hydrogens. My molecule has 12 hydrogens. This is really the ratio. 3-to-1 is not telling me that I have 3 hydrogens here and 1 hydrogen here. It's really telling me that I've got 3 times as many here as here. But to work out to 12, right, I have to account for 12 hydrogens in my molecule. What I'm really going to say is that a 3-to-1 ratio, we can get that by 9 here and 3 here, right? That adds up to 12, and that's a 3-to-1 ratio. So integration, the area underneath these curves is equal to, sorry, let me step back. The ratio between the areas underneath these curves is called the integration, and the ratio between those areas is the ratio between how many hydrogens this signal represents versus how many this signal represents. That's integration. Integration tells us how many hydrogens each signal represents. Now there's a third thing in proton NMR that's kind of similar to something we saw in carbon-13 NMR, but kind of different, and that's splitting. Now in carbon-13 NMR, we were not concerned about carbons splitting other carbons because only 1% of all carbons were carbon-13, and so that's not an issue. We were concerned in the off-resonance decoupled or the gated decoupled, or there's some other experiments, with how hydrogens affect carbons. Because hydrogens, all essentially, well, not just essentially, all by definition hydrogens are little magnets that will affect the carbons. And so the splitting in the carbon-13 NMR, in the off-resonance decoupled carbon-13 NMR, told us how many hydrogens were attached to that carbon. Now here we're looking at signals for hydrogens, not carbons. Now what affects them? This hydrogen is not really affected by the carbon because all of the hydrogens are NMR active, but only 1% of all carbons are. And so really the hydrogen 99% of the time is next door to a carbon-12, and so what we're going to see is a signal just for that hydrogen with no effect of adjacent magnet. Now if you were to blow this picture up really big and this, have a really good resolution, you might see a little blip here that was 1% the size of this, and you will see that in, if you have a really good spectrometer and you blow up the signals big and have good resolution. But usually you can't even see that. It would just be a little blip just right to the side of this. Instead, what's going to affect this little magnet is other little magnets nearby, and specifically we mean other hydrogens. Because if there's this hydrogen here has one hydrogen next door, that's a little magnet. If it has 0 hydrogens next door, there's no effect, and therefore we see no splitting. If there is one hydrogen next door, that one is a little magnet, and so remember our analysis when we did splitting before. We said the blue, representing this one, is a nuclear magnetic moment in an external field. The adjacent nuclear magnetic moment could either be, if we just have one of them, it could be the same or the opposite. And we've got 2 different ways to be. Those have 2 slightly different energies, and so what we see is a doublet. Notice this is telling me something a little bit different than we saw in the carbon-13 NMR. This is telling me how many hydrogens are on the next position over. If we had 0 hydrogens on the next position over, no splitting. If we have 1 hydrogen on the next position over, we get splitting. If we have 2 hydrogens on the next position over, we get splitting. But now, in this case, our nuclear magnetic moment for the blue hydrogen, the big blue arrow, has 2 red arrows adjacent to it, which can either be with and against, or against and with, or both against. The pattern is going to be completely statistically random, which means there's going to be equal possibilities of each of these, but the energy for having 1 adjacent small magnet with and 1 against is the same as the energy for having 1 against and 1 with, and so the pattern we see is really a 3-signal pattern, because we really have 3 different energies, but there's twice as many ways to have this central energy. So we'll see the triplet pattern, the short, tall, short pattern that we also saw in the off-resonance decoupled carbon-13. If our hydrogen has 3 hydrogens next door, well, now there's 8 possible ways to account for 3 adjacent nuclear magnetic moments, but these 3 are all the same energy of each other, and these 3 are all the same energy of each other. It's the same analysis we did before. We get a 1 to 3 to 3 to 1 peak pattern. The difference in energy between this and this is the same as the difference between this and this is the same as this and this. So we'll see these equally spread, short, tall, tall, short. That's a quartet. So proton NMR, we're going to see splitting anytime we see adjacent hydrogens. That is, hydrogens on the next carbon over. Turns out if there's an OH next door, it doesn't get involved in splitting. It just because of hydrogen bonding is going to cause an effect there. But it's the next carbon over has hydrogens. Okay, aren't always that simple. Because take, for instance, this molecule, pentachloropropane. Or I should really just say 1,1,2,3,3 pentachloropropane. And let's focus on the hydrogen in the middle, the one in blue. It's next door to a hydrogen on this side, and it's also next door to a hydrogen on this side. So it's affected by the little magnet on this side and the little magnet on this side. But this is a completely symmetrical molecule. Cut it in half this way and say this side is exactly the same as this side. And so therefore the effect of being next door to a magnet on this side is exactly the same as the effect of being next to a magnet on that side. By the way, that effect is called the coupling constant. It's used, J is the letter that's used to abbreviate coupling constant. So if we have this pattern of having two adjacent little magnets of exactly equal effect, well, we're going to see a triplet because we've got four ways to arrange those, but the two middle ones, with and against and with, are exactly the same in terms of energy. And so what we're going to see in this case is a triplet. Really the exact same as when our H was next door to two H's on this side. But what if it's not symmetrical? So, for instance, let's take well, it's 1,1-dibromo 2,3,3-trichloro-propane would be the name of this. This molecule is not symmetric. Again, this hydrogen is affected by a hydrogen on this side and a hydrogen on this side. But in this case, the effect, because it's not symmetric, should not be expected to be identical. So the coupling constant, the J value, for being next door to the one on this side, is not the same as the one on that side. And I'm going to demonstrate that, I'm going to kind of symbolize that as arrows of different sizes. I am not, at this moment, making any claims about which one affects it more. I'm just trying to make these different. But if things are the same, they're the same, and if they're different, they're different. So this is going to be one energy. This is going to be another energy. But this one is not the same as this one. With and against and with don't add up to the same. Now if those two coupling constants were the same, the top case, with and against and with were identical situations. But here they're not. And so instead of seeing a triplet, and then there's both against. So instead of seeing a triplet, what we're going to see is four distinct energies, which is going to lead to four distinct lines. We call this a doublet of doublets. So let's look in the top red. Here we see a pattern that has, instead of a triplet, we actually have two sets of two. There's actually two coupling constants. The distance between these is one of my coupling constant values, one of my J values, and the distance between the center of this pattern and the center of that pattern is my other coupling constant. So one of my hydrogens is going to break into two, my signal into two, and then my other hydrogen is going to break each of those into two. So we could sort of say that if I've got two CHs on either side, one splits it into a doublet, and the other one splits each of those into a doublet. And we call this a doublet of doublets. Now, depending on these coupling constants, depending on the values of these J's, this pattern might look a little bit, there's different ways this pattern might look, but it's still two sets of doublets. If one is much bigger, so if J1 is much, much bigger than J2, we're going to see something like this. We've got essentially two pairs, and they're kind of far apart. Or, you know, they're distinct. They're easy to see. But hold up two fingers like a peace sign on each hand and start moving them closer to each other. Okay? In green, we see a case, what if the J1, that is the distance between the center of these, is exactly twice the distance within each pair? Then we'll see a pattern that looks kind of like this, where all four are kind of equally spread. If J1 is less than that, but still more than J2, we're going to see a pattern where our two doublets are starting to get very close to each other. If J1 and J2 are the same, the two of my signals start to merge. So really what's happening here is I've got this pair and this pair. As I'm pushing them closer and closer, in the middle they start to merge and become one signal. Really, that's indistinguishable. If J1 and J2 were identical, really that's what we have in a triplet. Two hydrogens where each has the same exact effect, and the sum of those is the triplet pattern. And then if I keep bringing my two peace signs, so if you held up your fingers, I know I'm doing this and I'm recording this, right? So you're not seeing it. But if you brought your hands closer and closer together, eventually they're going to start overlapping. That's what we see down here. And if they completely overlapped, that happens when one of your coupling constant would be 0. What you just see is a doublet. They collapse all together. All of these count as doublets of doublets, though this blue case where J1 equals J2 is really it is a triplet, and this green case we would call it doublet. Okay, let's be a little more complex. What if our hydrogen, highlighted in blue here, was next door to a CH on one side, the red, and a CH2 on the other side? Now we're adjacent to a total of 3 little magnets, right? But the red one and the green one have different arrow sizes. It could be that J1 is bigger than J2. Or it could be that J2 is bigger than J1. And I'm going to symbolize these as bigger and smaller arrows. I don't know yet, just from looking at the structure, which one it is. I would actually have to look at the spectrum to see which one it is. But if I was to look at these, having 3 magnets next door, they could be all with against, oops, this one should be with against with. Okay, I apologize for that. This one should be down and this one up. But that doesn't matter ultimately, because these two are going to have the same energy. With against, against with, against with, against with. This should be against with, against, and against with. So I should flip one of these and flip these. And then all against, relative to the blue. But these two are going to be identical energies to each other, and these two are going to be identical energies to each other. Or I could be with against, with against with. Man, this is what happens with cutting and pasting. Against with against. This should be against with against, and well, this one. No, I'm sorry. I didn't do any cut and paste. Anyway, there's 8 ways of putting these guys together, but again, some of them, these two and these two, turn out to be identical energies. So they're going to be grouped. This is going to turn out to be a shorter signal, a taller signal, a shorter signal, a shorter signal, a taller signal, a shorter signal. If the pattern was like this, what we would expect to see is a shorter signal, a shorter signal, a taller signal, a taller signal, a shorter signal, a shorter signal. Or patterns that look like this. This one looks like a triplet. All right, a triplet is short, tall, short, but then each of my peaks of my triplet has been split into 2. And so we would call this guy a triplet of doublets. On the other hand, the other way of depending on which J is bigger, I could have something like this, where I get essentially something that's 2 sets, each of which a doublet, which has been split into triplets. And so we would call this one a doublet of triplets. Now, I don't want you to be overly confused by that. That's something that students sometimes get upset by because it seems unclear whether something is a doublet of triplets or a triplet of doublets. In both cases, notice that there is a total of 6 lines. In both cases, notice that 4 of them are shorter and 2 of them are taller. The difference between these is really just a difference of the spacing. For instance, how many circles are here? Well, 6, right? That's a total of 6 circles. But would you say that that's 2 sets of 3 or 3 sets of 2? Well, you could call it either, right? They're spaced equally, and so, 2 times 3 equals 6, and 6 times 3 equals, 2 times 3 equals 6, and 3 times 2. 2 times 3 and 3 times 2 both equal 6. All right, let's look at it in red. Would you call this 2 groups of 3 or 3 groups of 2? Well, it's still 6 signals, but it would seem most clear to call this one 2 groups of 3. Let's look at it in green here. Would you call this 2 groups of 3 or 3 groups of 2? It's still 6 signals, but it seems like you would call this guy 3 groups of 2. Now notice I haven't changed the circles at all. Well, I've changed their colors just so I could talk about the blue set, the red set, and the green set. But they all have 6 circles and I haven't changed the diameters of the circles in those cases. But the spacing has been changed, right? And so based on the spacing, I would call these guys, a set of 6, 2 sets of 3, or 3 sets of 2. That's the same thing that happens when we're talking about triplets of doublets or doublets of triplets. In the top line here, we see 6 signals, but the spacing has been changed. So we call this one a triplet of doublets, and we call this one a doublet of triplets. But it's really just like on the previous slide, where we had 6 circles, and we referred to them as 3 sets of 2 or 2 sets of 3, depending on the spacing. So don't be overly worried about that. But this can get even more complex, because that's what happens when one of your J values is much larger than the other. But remember when you held up peace signs on each hand and you brought your hands closer together, eventually they start overlapping. The same thing could happen if you held up 3 fingers on both hands and you started bringing your hands close to each other. So if they were far apart, you'd say you had 2 sets of 3. But as you start bringing them close to each other, they can start overlapping. And so in the bottom here, you see something that looks complex. But don't let that worry you, because if we look at this, notice we still have 4 short lines and 2 tall lines. It's just the spacing has been changed a bit. And if I was to color code this, if I colored 3 of my lines red and 3 of my lines purple, now totally ignore the purple, and if you look at this, short, tall, short, hey, that's a triplet. And if you ignore the red and just focus in on the purple, you see short, tall, short, equally spaced. That's a triplet. What's happening here is you've got your 2 triplets, but they're starting to overlap each other. So, this is still a doublet of triplets. It's still 2 sets of triplets, and they're just really close to each other. The difference between these names, triplet of doublets and doublet of triplets, really comes down to who has the bigger J value. I don't want to worry about that over much. Just when I've got these patterns, I can tell that I've got a CH on one side and a CH2 on the other side. Unfortunately, things can get really, really confusing when you have multiple hydrogens. Imagine you had 3 hydrogens on one side and 2 hydrogens on the other side. Being next door to 3 hydrogens splits you into a quartet. Being next door to 2 hydrogens splits you into a triplet. So what you'll get in that instance is a triplet of quartets, or a quartet of triplets. That's 12 lines, but imagine those start overlapping each other. The J values are close enough in value that they start overlapping. You might get something like this. This pattern is very hard to interpret. By the way, this pattern is just an expansion of this little blob. That guy right there, if I was to blow it up, looks like this. We're not going to bother. In this class, what we're going to do is we're just going to refer to that as a multiplet. In fact, when we're looking at a hydrogen NMR, we're pretty much going to start with looking at things as singlets, doublets, triplets, quartets, or things more complex. Now sometimes those things more complex will be obvious, like I've got a doublet of doublets or a doublet of triplets. But really, in reality, in real spectra, you go into the lab and you measure a molecule, those things that have hydrogens on either side are going to tend to be harder to interpret. And so what we're going to do, at least at first, is just refer to those as multiplets. And like I said before, when you're doing spectroscopy, start with the clear. Start by looking at the spectrum and saying, if we're trying to interpret the splitting pattern again tells us how many hydrogens are in the next position over. We're going to look at the things that are singlets, doublets, triplets, and quartets. And then, after we interpret those, it'll be pretty obvious because of the way things fill in. So when we're interpreting proton NMR, we're going to look for three things. We're going to look for chemical shift. Chemical shift tells us about the bonding environment. That is, it tells us whether the hydrogens are bound to sp2 or sp3 hybridized carbons or other elements. It'll tell us within the sp2 region. It'll tell us whether we're next to alkenes or alkenes or aromatics. That is benzene, things like benzene. It'll also tell us if there's strongly electronegative elements nearby. I don't want you to try and learn a whole bunch of numbers. I want you to learn basic trends. Look for regions on the periodic table and on regions within the graph, within the spectrum, and then within those regions whether things are more to the left or more to the right. Integration tells us how many hydrogens that particular signal represents. And remember, the ratio between the sizes of the peaks is the ratio between the number of hydrogens. So sometimes if I've got a ratio of 1 to 2, it might be really that I've got 2 hydrogens represented by one signal and 4 by the other, or 3 and 6, or 20 and 40 for that matter. And then there's splitting, which is always present. Unlike the carbon-13 NMR, where we had to do a specific type of experiment to see splitting. Splitting's always present, and it tells us how many hydrogens are on the next position over. This is pretty much always the most complex thing in spectroscopy, and so it's the thing that we should turn to last. And even within splitting, I always counsel people to start with the simple spectra, the simple signals like singlets, doublets, triplets, and quartets, and not be so concerned about the ones that are doublets of triplets and triplets of quartets and doublets of doublets of doublets and all kinds of confusing things until I've interpreted other things, because oftentimes I don't have to go there.